we try to elaborate on that a little bit more. So there's the concept of unstable neighborhood. That means that concept of neighborhood becomes meaningless. So what is an unstable neighborhood? Well, a nearest neighbor query is unstable for a given threshold epsilon if the distance from the query point to most data points is less than 1 plus epsilon times the distance from the query point to its nearest neighbor. So let's take to most data points to all data points. So consider this one here. This is our query point. So this is the nearest neighbor, yeah, this is the nearest neighbor distances here, and say this one here is the threshold, the 1 plus epsilon, yeah. So the neighborhood is stable if most of the other points are not within this range here. This is what the definition says, yeah. So if the distance from the query point to most other points is less than this one here, then it's getting unstable. So if all those guys here would be in this circle here, in this dashed circle here, the whole thing, the neighborhood would be unstable for Q. Yeah, that means all the other points here. So if the d max, that is the maximum distance to all other points, if the d max would be smaller than d min plus times 1 plus epsilon, then the whole thing would be unstable. So all the other guys would be in this range here, saying that the distances between the nearest neighbor and the farthest neighbor is the difference between those two distances is so small that it's not suitable to somehow differentiate between the nearest neighbor and the farthest neighbor. Yeah? And here is an example where that holds. So here the query point is somewhere near this circle of the center of this circle here, where the other points are drawn from. So this guy is obviously the nearest neighbor, and then all the other points are within a very short range of this nearest neighbor distance. And in this case, then the nearest neighbor, the nearest neighborhood is unstable. Yeah. Okay, and it can be shown that with growing dimensionality, the probability that the query is unstable actually converges to 1. Yeah. So in high dimensional space, it's extremely likely that we have something like this here and not something like this here. So we have an unstable neighborhood instead of a stable neighborhood. So here is the theorem for that. So we consider a d-dimensional query point Q and n d-dimensional sample points x1 to xn. They need to be independent and identically distributed, and then we define d min is the distance to the nearest neighbor. So again, look at this one here. This is our query point. This is the nearest neighbor. D min is called, as before, the distance to the nearest neighbor, to the next neighbor, and d max is the distance to the farthest neighbor. So the point that is farthest away from Q in terms of the distance function. And we use the L2 norm here. Yeah, and then there is the theorem. So if the precondition holds, which is actually just saying that we have independent and identically distributed features and points, then for any epsilon, the probability that d max is smaller than 1 plus epsilon times the d min, which is the unstable neighborhood definition, becomes 1 with increasing dimensionality. Yeah? So if the precondition holds, all points converge to the same distance from the query, like in this more or less like in this example here. And that holds true if the precondition holds for any high dimensional data set. So here is a visualization of this theorem. So we look at the pairwise distances of a sample of 105 instances drawn from a uniform distribution, normalized, whatever. Okay, and here you see on the x-axis the dimensionality grows, and here is the distance. Well, the normalized distance, of course, does not grow, so, or should not grow too much, so it remains stable because we normalize it by 1 divided by this factor we saw that the norm, the distances, will grow by a factor of d square root of d. So if we normalize it by 1 times this one here, it should be constant, which you can see more or less here. Yeah, so here is the solid red line is the mean, and the dashed line indicates the standard deviation. And you see the standard deviation remains more or less constant, and the mean, of course, also because of this normalization here. And now here is the empirical evaluation, that the pairwise distances actually measured from the samples, the minimum nearest neighbor, so the d min distance is the blue one, and the d max distance is the green one. And you see, when you increase the dimensionality, the d min and d max distances, they become more and more similar. They converge to the mean, and that's exactly what this concentration problem states, and why the neighborhood concepts become meaningless, because the neighborhoods get unstable. So just one thing of caution, please be very clear about the precondition of the theorem here. Yeah? So we said that we consider points, independent points, and identically distributed. Especially the features are the features, not only the points, but also the features are independent and identically distributed. Yeah. Take the other one. So consider feature space of d relevant features for a given application. So truly similar objects display similar distances in most features. In this case, I do not have any problems. But now, if I add d times c additional features, being completely independent of the initial feature space, having nothing to do with the application, well, with increasing c, obviously the distance in the independent subspace will dominate the distance in the complete feature space. Yeah. So if I increase the c, the bad influence of these independent and irrelevant features will become more and more apparent, and the bad influence means we become more and more distance concentration, and the neighborhoods will be more and more unstable. Yeah. So the question, of course, is how many relevant features must be similar to indicate object similarity, or if I used distances the other way around. That is sometimes very hard to answer this question. But anyway, with increasing dimensionality, the likelihood that two objects are similar in every respect gets smaller. Yeah? That means if I increase the feature space, the dimensionality of the feature space, the probability that I add features that follow this the precondition of the theorem increases. Yeah? So the more features I add, the higher the likelihood that those features follow these preconditions. So the higher the likelihood that I have this concentration problem. That's the point. You know?